One of the things that we want to very often do in inference is we want to estimate the value of a parameter, the very common thing. And so this boils down to the question of how do we get estimates for parameters? Okay. The first thing you have to understand is that all random variables, their distributions depend upon parameters. Okay, so if you look at the binomial distribution, it depends on the parameter p, right? Poisson depends upon the value of lambda. The normal distribution depends upon two parameters, okay? So in order to uniquely identify this specific distribution, you have to give the values of the parameters. The problem with this picture is that we almost never know the values of these parameters. Suppose you flip a coin 10 times. You might think, well, that's binomial 10 with p equal to a half. But we don't know that p is equal to a half exactly. And in fact, even things that we think we know, very often we don't. There's a very famous Stanford statistician, Diaconis, that proved that in coin flips, p is not equal to a half. Okay, so we generally don't know the values of these parameters, so how do we get them? Well, we do inference. We take a sample and we estimate the parameter from that sample, right? That's the inference. We take a sample, we get an estimate, and we say we think this is true for the entire population. How do we do this? Okay, well, we're going to see how, but one term you should be aware of is that whenever we estimate just the value of the parameter, we call it point estimation. And this is to be distinguished from interval estimation. Okay, so what I'm trying to say here is that when we estimate the value of a parameter, we only get a single value, a point. Very often we want to put an error bar around that estimate because we know the estimate is almost surely not going to be equal to the value of the true parameter. So when we put that error bar around there, sometimes we call that interval estimation or confidence interval. But right now we're only interested in point estimation, okay? And so we're going to see there are two main methods for point estimation: the maximum likelihood estimator, which we abbreviate by MLE, and the method of moments estimator, which we abbreviate by MOM. And we're going to see how both of those work. Okay? So we want to first ask ourselves, what properties should a good estimator have? There's a lot of different estimators for the same parameter. Okay, so estimators are not unique. There's not just one, but there generally is a best one. Okay, and a lot of statistics boils down to showing that the estimator that you're using is in fact the best. How do we define best? Well, we're going to go ahead and we're just going to let phi be some general parameter of interest and phi hat be its estimator. And we're going to notice that estimators always put hats on them, so I have to be able to distinguish between the estimator and the actual parameter value. So I put a hat on the estimator, okay? And we're going to notice something very important. Phi hat is an estimator from a random sample. Therefore, it's a random variable. And every random variable has its own distribution. Okay, so all estimators are random variables and they have their own distribution. Okay, so there are two properties given that phi hat has its own distribution. There's two properties we'd like the distribution of phi hat to have. The first is that we would like phi hat to be unbiased. And unbiased means that the expected value of the estimator is equal to the true value of the parameter. Okay? And so sometimes we say we want the estimator to be we want phi hat to be an unbiased estimator for phi, meaning that the expected value of phi hat is equal to phi. Okay, why would we like this? Well, think about it for a second. What is the expected value? The expected value is the value that you would most likely expect to see. Well, what value will we most likely expect to see? We'd like it to be the value of the true parameter, because that's what we're trying to estimate. Okay. That's an important property, but that's only half of the story. Notice that because phi hat is a random variable, it has a distribution. So we'd like the variance of that distribution about phi to be as small as possible. Okay. So we would like phi hat to have the smallest variance, the distribution for phi hat, to have the smallest variance among all other estimators for phi using the same sample size. Okay. And again, why is that? Well, look at the distribution for two different estimators, okay? We're going to say their mean is phi here. Well, you know, we're using mu, but same difference, right? The mean for the first estimator is equal to the mean for the second estimator, which is equal to phi. But notice that this distribution is a lot broader. It has a bigger variance. Okay, so this estimator is more likely to be further away from the expected value than the first distribution, because these values are more tightly clustered around phi. Okay, so we don't want the values of the estimator to be able to go too far from the expected value, and of course the smaller the variance is, the less likely they are to be further away. Okay, we also want the estimator to be easy to compute. Usually this is a secondary consideration, with one exception, and that is when you're doing real-time applications. So as an example, people use machine learning to teach computers how to play ping pong. Okay, there is a situation where computational time becomes an issue. But if you're not doing a real-time application, computation is usually a secondary consideration. Okay, the first method we have is called the maximum likelihood estimator. How does it work? Well, what we do first is we start with the joint PDF or PMF for a random sample. Okay, so we then go ahead and we find the value of the parameter which maximizes the PDF or the PMF for that random sample. And let me kind of show you how it works. Okay, so let's suppose we're trying to estimate mu from a random sample where the variables are distributed like a normal distribution with mean mu, standard deviation sigma. I'm always going to let the sample size be n. Okay, so I'm not going to bother putting I equal 1 to n here. Okay, so we find the joint PDF. Well, we know the PDF for each individual random variable is this, and we recall that when we have independent random variables, the joint PDF factors into the individual PDFs. Okay, and so we can simplify that, and we end up getting the following. Okay, now notice that mu is the only variable here. The xi's come from the random sample. Okay, and sigma is considered known, and I want to find the value of mu that maximizes this, so it's probably a good idea to get it out of this exponent. Okay, but before I do that, I'm going to rewrite the PDF now as a function of the parameter. Notice that the random sample values are now known. This is for a known random sample. Mu is the only unknown variable. Okay, and so now I'm going to go ahead and I'm going to take the log of both sides, and this is sometimes called the log likelihood function. Okay, if you take the log of both sides, you get the following expression. Now I want the mu that maximizes this function, so what do? Well, I'm going to go ahead, I'm going to take the derivative with respect to mu, set it equal to 0, and find the max. Okay, and when you do, I claim when you take the derivative, you're going to get the following quantity. That's easy to see because there's no mu dependence here. Okay, and when you go ahead and you set the derivative equal to 0, now this becomes the MLE. This is the condition that the MLE satisfies, and you solve for the MLE and you'll get x bar. And that makes sense. The maximum likelihood estimator for the mean will be the sample mean, right? Wouldn't the sample mean be the best estimator for the population mean for a given sample? Of course. Okay, what about the method of moments? Well, it's much easier. Here's all we do. We're going to first of all recall what we know about population and sample moments. So we're going to say that the jth moment of a distribution, or the jth population moment of a distribution, is the expected value of x to the j power. I'm going to call this the distribution moment. Okay. The jth moment of a sample is just going to be the sample mean of x to the j. Okay, I'm just going to take the average value of x to the j from the sample. Okay, and now we're ready to see how the method of moments works. Okay, we start off, we put the parameter of interest in terms of the distribution moments. Okay, this is the hardest step usually. So for the mean, we know that the mean is equal to the first moment, right? We know the variance is equal to the second moment minus the first moment squared. Okay, so this is the second distribution moment minus the square of the first distribution moment. Okay? And now all you do is you substitute the sample moment for the distribution moment. And that gives you your estimator. So notice that if mu is equal to the first distribution moment, mu hat is equal to the first sample moment. Okay? So all I do is I'm just replacing mu1 with capital M1. Okay, and that's what's getting me from the parameter to the estimator of the parameter. Okay, the hat there tells me I'm working with the estimator, right? What about the variance? Well, the variance is mu2 minus the square of mu1. So what do? I just substitute for mu2 with capital M2, mu1 with capital M1, and I get the method of moments estimator for the variance. Okay. So notice that all you're doing is you're replacing mu with capital M. Okay. Now, what are some of the pros and cons? Well, the MLE has a lot of pros. It tends to be unbiased, or at worst asymptotically unbiased. It has the asymptotically smallest sample variance. This is called the Kramer-Rowell theorem. The sample size gets larger, the estimator has a normal distribution, and there's actually one property I didn't put in here that's very important, and I'm going to add it right now actually. I should have added it before. It's that if we know the MLE, okay, so if we know the MLE for phi, so if I know the MLE for phi, this is called the invariance principle. This implies that the MLE for a function of phi, okay, so I'm just going to take some function of phi, and I want the MLE of this whole thing right here. Probably won't let me do it. So I want the MLE estimator of this. It says that the MLE estimator for a function of phi is equal to the function of the MLE for phi. This is called the invariance principle. It's a very important principle. Okay? And so this is one that we like to use a lot. So in other words, if you know, suppose phi was an angle. Okay, if you know the MLE estimate for the angle, then if you take sine of phi, the MLE estimate for sine of phi is sine of the MLE estimate for phi. Okay, it's as if the MLE distributes across the argument of the function, called the invariance principle. Cons of the MLE is it can be computationally intensive. And again, if we're not working with real-time applications, it's not so much an issue, but it can be actually. The MOM, method of moments, it's computationally easy, but it can be biased. It has some guarantees here with respect to variance and bias, but they're weaker. And unfortunately, it requires a lot more probability theory than we have to be able to actually be able to actually address that. Okay, let's look at a sample problem. Suppose we want the estimator for P of a binomial distribution. Let's find the MLE estimator. Well, first we're going to find the joint PDF, so it's the product of the individual PDFs, okay, for this random variable. I'm going to simplify it, okay, and I'm going to represent the sum of the xi's by nx bar. That's a nice little technique we can use. Okay, I'm going to then take the log of the PDF to get the log likelihood function, and I'm going to call this whole quantity here capital C. The reason why is, as far as P is concerned, it's not a function of P, so this is just some constant. Okay, so I end up getting the following. Take the derivative of the log likelihood function. Okay, I set it equal to 0 and I solve for P hat. Okay, so as soon as I set it equal to 0, P becomes P hat, and I solve for P hat, and I get P hat is equal to x bar over n. And that makes sense. What is the probability? Well, it's the number of successes divided by the number of trials. So it should be, so P hat should be the average number of successes divided by the number of trials. It makes sense, right? Okay, what about the method of moments estimator? Well, it's much easier actually. Remember, first we find the relationship between our parameter and the distribution moments. Well, we know that if x is binomial, mu is equal to np, and mu is the first moment, right? So I'm going to solve for p. P is equal to mu over n, and of course mu is the first distribution moment over n. Okay, and remember, all we do to get from the parameter to the estimator is we just replace mu by m. Okay, so it's p hat, the method of moments estimator for p, is equal to the first sample moment over n, and we see the first sample moment is x bar, so the method of moments estimator for p is x bar over n. Notice that the method of moments and the maximum likelihood estimator gave us the same result. That's not always true. Okay, it's sometimes true, but not always. It just happened that it was in this case. Okay, for homework, here's what you're going to do. You're going to look at two problems. The first is where x is distributed like an exponential random variable, and you want to find the maximum likelihood estimator for lambda and the method of moments estimator. The second is where x is going to be a gamma distribution with parameters alpha and beta, and I should make that alpha and beta. And what we want to recall is that when we have a random variable that's gamma distributed, this is the PDF. Okay? And so now we want to show the MLE for alpha, supposing that beta is known, the MLE for beta, supposing alpha is known, and then the MLE for alpha and beta, supposing neither one is known. Okay, so here you're going to be taking two partials, right, and setting it equal to 0. Okay? So here you're looking at a function of two variables. How do you find the maximum of a function of two variables? So you want to go back and use your multivariate calculus. Notice that we can find the method of moments estimator for alpha and beta without having to do all this like we had to do for the MLE. And here you want to look up the mean and the variance for a gamma distribution in terms of alpha and beta, and recast alpha and beta in terms of the distribution moments. Okay? And that's pretty much all for determining estimators for distributions.